Hi, this is Nick Marchuk, and in this series of videos, I will be designing a printed circuit board using the software Eagle. This is for my April 2022 class, Advanced Mechatronics at Northwestern University. I've made these videos every year for a while now, and Eagle changes a little bit each time, and my board design is a little different each time. So this will be specific to my class this year. If you're following along for fun, you could pick up whatever little tidbits there are. If you're following along with class, I'll design everything from scratch. So in the first video, I'm going to show you all the parts that we need and how to make the components in an Eagle library. After that will be another video where we take the parts and make a schematic, connect all the components. And then in the third video, I will do the board layout, lay out the copper traces, and then generate the Gerber files that we send to the manufacturer. So let's start backwards. Here we see a board that I've already designed for this year, so I'm going to design something like this right now. We have a PIC32MX 170F256B as our microcontroller in the middle. We're going to get power either from a battery connector or from a USB to UART breakout board from Adafruit. We'll have a slide selector switch to determine whether we're getting power either from the 6-volt battery or the 5-volt USB cable at a given time. That'll go to a Pololu 3.3 volt regulator to supply 3.3 volts to the rest of the board. We'll have a snap microchip MPLAB snap as a programmer and debugger for the PIC. So the PIC is going to connect to the snap and the USB to UART. We also have a I2C SD 1306 OLED display over here so we can see things. We've got a user LED, a power LED, a reset button, and a user button. The resistors necessary for those, the capacitors to make the whole thing work. And then we break out all the rest of the pins on this board to the side so that we can have a shield plug-in on top. I will design another board later that plugs into the top of this board and gets us access to even more goodies. So we have to keep that in mind. Basically, we could put any part wherever we want, except for these headers. I would like the headers starting from A0 to A1 to B1 and so on this side, and B15, B14 on this side. This PCB will be 50 by 50 millimeters, and here are the locations of the A0 and B15 pins, and everything else is 0.1 inch below there. You can take a look at the schematic real fast. So here's our PIC32 down here. We've got the support capacitors to make it work. We have a button on the MCLR pin, that's the reset button. We have a button on B4 and an LED on A4, those are user button and user LED. I have just a regular red LED from 3.3 volts to ground to act as our power LED. Here's our 6-volt battery connector that goes to our slide switch that's determining whether we're using 6 volts or the 5 volts from our USB to UART chip. That guy's over here. I have some extra signal pins broken out for the voltage input coming from our slide switch, the 3.3 volts and ground, as well as some pins to SD and SCL to access our I2C port. So what are we going to do? We're going to design a part in Eagle in the library for our PIC. Then we'll make a part for the debugger for the snap, as well as the pins on the bottom of this CP2104 UART friend from Adafruit. Here's what the I2C display looks like. Here's the dimensions and the pins for our voltage regulator from Pololu. Here's the recommended layout for the slide switch. And then I like to take advantage of SparkFun's Eagle libraries to grab the pins that we'll use for the header pins that will go to the regulator and the display and the UART connector and the snap. So we'll design some things from scratch, we'll grab some things from Eagle libraries, and we'll do a mix and match of designing our own schematics and stealing some pins from SparkFun to make this all work. So I'll start by going into Eagle, and I'm going to make a new project in my folder 2022, and I'm just going to call that ME433 video. And in that project, I'm going to make a new library. And so we're going to work from right to left. We're going to make a symbol for the parts that we're designing. Then we're going to design the footprint. That's what it looks like on the PCB. And then we'll design the device that connects the footprint to the symbol. Let's start with the most complicated device. Let's start with the PIC. So I'm going to say add symbol, and this is going to be the PIC32 MX 170F 256B. Probably don't have to be so specific, but might as well. Here's my schematic editor. I'm going to put that on the right side of my screen, and I'll grab the picture of the PIC for the left side of my screen. Okay, you can probably notice there's a little plus symbol right in the middle of the schematic editor. I'm going to make all of my pins symmetric about that point. That'll be the point at which I can grab this part and move it around in the schematic. So I need to add 28 pins. So I'll go to the pin tool, and wherever I click, I'm going to add a pin. So I'm going to give myself a gap. And maybe first I'll do 7 pins on the top. 1, 2, 3, 4, 6, 7. 1, 2, 3, 4, 5, 6, 7 pins. And then rather than make all 28, I'll use the group tool. I'll grab these 7. I'll use the copy tool. I'll hold Control and right click on my group to copy another 7 pins. So I have 14. Now I'll group all 14 together and copy, Control, right click, and then I will right click to rotate. Now I'll drop 28 pins. Now the secret here is that I'm going to name every single pin with its function as we see it on this pin function page. I'm going to name the pins the pin number dot the functionality. That way I'll be able to remember what order the pins come out and what functions we're going to use. And I've already determined which pins are kind of extra special for this particular project. So I'm going to go back to actually my schematic and steal these pin names. So for instance, pin 2 is A0 and a bunch of other things. Pin 4 is B0. It's also my data line for the NPLab snap. That's the programmer. So I'm going to give the pins that I don't necessarily have a specific function to the name of the pin, and the ones that I'm later going to use for a very specific function, I will also tag that on there so I remember. Okay, so back in Eagle, I will use the name tool to name the first pin 1.MCLR. That's our reset pin. Second pin is 2.A0, which will be just a generic pin for us. 3.A1. 4.B0/PGD. So that was specifically going to the snap. Looks a lot like an O, not a 0. Okay. Pin 5 is B1/PGC. That's the clock line from the snap. Pin 6 is B2. Pin 7 is B3. It's a reprogrammable pin, and eventually we're going to reprogram it to be U1TX to talk to our computer. Pin 8 is ground. Pin 9 is A2, and we will make it U1RX. Pin 10 is A3. Pin 11 is B4, and we're hooking that up to our user push button. Pin 12 is A4, and we're going to hook that up to our user LED. Pin 13 is a power supply pin. And pin 14 is B5. Then on the other side of our chip, pin 15 is B6. Pin 16 is B7. Pin 17 is B8, and I'm going to use that as my I2C clock line for I2C1. Pin 18 is B9, and we'll be using that as the data line for I2C1. Pin 19 is a ground pin. Pin 20 is the VCAP pin. We have to put a 10 microfarad capacitor there, and we would read 1.8 volts. See, pin 21 is pin B10. We'll use that as U2TX, and hopefully we'll figure out how to use that to talk to another microcontroller. Pin 22 is B11, which will hook up to U2RX. Pin 23 is B12. Pin 24 is B13, and that is capable of being output compare 5, PWM. Pin 25 is B14, and it's capable of being output compare 3. Oops. Pin 26 is B15. We use that as output compare 1. So I have 3 out compares, 2 for driving brushed DC motors and 1 for driving an RC servo. Pin 27 is AVSS. That's specifically the ground for the analog to digital converter inside the PIC. And pin 28 is AVDD, specifically the power supply for the ADC. So after we've drawn and named all of our pins, we should probably go back and just double check that we didn't do anything wrong. So MCLR A0, A1, B0, B1, B2, B3, VSS, A2, A3, B4, A4, VDD, B5, B6, B7, B8, B9, VSS, VCAP, B10, B11, B12, B13, B14, B15, AVS, VD. Okay. After you make such a complicated chip, I like to draw a line around it, so we remember that all these pins are related to each other. And then finally, we add a text tag with caret all caps name and caret all caps value. So we could use the name and value tool when we add this to our schematic to change its name and value. Sometimes you like to have that inside the chip, so maybe I'll just bump up that there. And I'll give this a name. So we're back in our library. We have a schematic for the PIC. Now we need a footprint. The PIC we're using is the DIP version. I don't want to have to make a DIP chip from scratch though, so let me go find a footprint that somebody else has made for a DIP 28-pin package and steal it. So we'll go to the control panel. I have my library open, and in my control panel I can go search the managed libraries that came with Eagle. And I'm looking for basically anybody who's made a DIP package before. So for instance, I'm pretty sure in the microchip library, they've included some chips. They don't have every single PIC, that's why we're making one from scratch. But some of the PICs that they have in there use this package, so we should be able to steal their footprint. So we want microchip. And so if we open up the tree structure for this library and scroll down past all of the devices to footprints, here are all the footprints that they've made for their PICs, and here's a it says DIL 28-3, so dual inline package, 28 pins with 0.3 inches between the package. That's the one that we want. They also have a 28-6. That'd be a really fat version of this chip. I don't think they sell those. So because this is open, I can right-click on the footprint that I want and say copy to library. And now I've got the DIL 28-3 in my library. And finally, I will make a device that makes the pins on my symbol line up with the pins in my footprint. So I'll say add device. I'll just call it PIC32. I'm going to add my symbol for the PIC. I will add the package. And finally, I have to connect them. So the nice thing about naming your pins in the symbol with the pin number is that they will line up directly with the pads, and I can just mash the connect button to make all the connections. I don't have to go back and look at the data sheet. Okay, so our pick is done. What do we want to do next? Let's do all of our connections between things that talk. So we'll do the snap, and then we'll do the USB to UART connector, and then we'll do the I2C display, because those will be very similar in that we will have to make a custom symbol, which is just going to be how many pins there are, and then we will steal their footprint from SparkFun. So the symbols I need the snap connector. The snap has 5 pins. 1, 2, 3, 4, 5. The first is MCLR. The second pin is power. Third pin is ground. And then I'd better check. Let's see. Pin 4 is PGD, that's the data, and pin 5 is PGC, that's the clock. Double check it one more time. PGD, PGC, great. And I'll give this a name and a value. And we'll draw our box. Okay, so let's do another one. Let's do the USB to UART chip. Now, normally I would call this exactly what it is. It's a CP2104, but because we're using the breakout board, I don't want to be too specific. A lot of breakout boards will have the same pins, so we could change to another brand. This has 6 pins. 1, 2, 3, 4, 5, 6. And if we look at a picture of the board from Adafruit, why don't we make pin 1 ground? I'll just leave that over there so I could reference it. .2 CTS 3.5 volts. So this is one of the ways we'll be getting 5 volts into the board is by stealing it from this connector. 4.TXD, that's the transmit pin out of this board. 5.RXD, that's the receive pin, the data going into this board. 6.RTS. Give it a name. Give it a value. Draw our box. Okay, how about we do our display? So the displays have 4 pins. 2, 3, 4. We will make pin 1 ground. Pin 2 is VCC, it's our power pin. Pin 3 is SCL, the I2C clock line, and pin 4 is SDA, the I2C data line. Good to note that this chip has the pull-up resistors required for I2C built in. Okay, that's good. Our voltage regulator. So far I've been treating chips as if they were just blocks, and I wasn't really distinguishing in from out. I'll keep doing that here, but notice that a lot of people will draw their voltage regulators. They'll put the voltage in on the left and the voltage out on the right, and then ground at the bottom. I want to kind of keep my orientation correct here, so I'm not going to make it look like that. Just keep making it look like a box. So we have got 4 pins. 2, 3, 4. Kind of been having my bottom pins have this being pin 1, so it'll be 1 point V out, 2 point ground, pin 3 is V in, pin 4 shutdown. We're not going to use the shutdown pin on here, but I'll draw it in anyway. And we've got a name, and we've got a value. Okay, so we've got our display, we've got our pick, we've got snap for programming, USB DOR to talk to the computer, voltage regulator for power. What else do we need? There's our snap. That's the USB to UART. That's the display. That's our regulator. Okay, why don't we finish those guys up? So for footprints, what we're looking for are holes that go into the breadboard, the print circuit board that match a breadboard layout. So that's 0.1 inches between them. And then we need to know the right drill size. So how big is this hole so that the male header pin can fit in? And I don't want to look that up. I'm sure there's a data sheet somewhere that tells me that. Instead, I know that SparkFun has a library of connectors that have the right size hole, so I'm just going to go steal that from them. Okay, so the SparkFun Git page shows you all of the different libraries that SparkFun provides, and you can go download their connector.lbr file and put it somewhere in your Eagle folder. So back in my control panel window in Eagle, I can go find where I put the SparkFun Eagle libraries and look inside the SparkFun connector library. And inside they've got these devices. So Con1 is a single pin in our schematic with a footprint with all these different sized holes. And if we look at their footprints, the 1x01, that's just a single hole, and this is appropriately sized to make it easy to solder, and a male header pin will fit in. So I'm going to start grabbing a bunch of these because I'll want them later. I'm going to copy the single pin and a double pin and a triple pin. Let's see, the display needs 4. The snap needs 5. The USB DOR needs 6. I don't know, grab a big one just in case. I'll grab something that needs 10. We'll see how far that gets us. So let's take a look at one of these for a second. If we click on the grid, we can see that the grid is currently 50 mils or 0.05 inches. So if we skip every other grid, we know that we're on 0.1 inch spacing. We're not distinguishing whether pin 1, sometimes we make pin 1 a square, but they're all circles. If I do an info on one of these, we see that they've picked a 40 thou drill and a 74 thou diameter wide. So that's the amount of green that we see. So that's a nice amount of space to solder on. So I don't really need to copy all of these. I could just make these from scratch as footprints and just use this size drill and diameter. That's what I really wanted to know from stealing this stuff from SparkFun. But they also draw a nice silk screen around here to remind you how big the plastic is on male header pins. So let me go open up the 1x04, and we will make a new version of this that is for our LCD. So I'm going to group everything together and hit the copy button. So I'm going to Control and right click. So now it's copied into my buffer, and I'm going to make a display footprint. Now I will paste, and I'll put it at an angle. And actually, in this case, I don't really particularly like the solder mask or the silkscreen that's in here, so I'm going to delete it and only keep the pins. So what I did was hide the pins before deleting everything else. And I'll go back and look at the picture. So this device is 0.5 inches tall and 1.5 inches wide. So I'm going to draw in silkscreen around it, maybe in nice big 16 thou box, just to remind myself how big this device is. So it's starting at minus 50 thou. So this should be 250. 250. So that makes this whole thing half an inch tall. And then to make it half wide, it started at 0.5, so that would be 1450. So that's now half an inch tall and 1.5 inches long. Should say the length somewhere. Length 1500. Great. Okay, and then maybe I'll add some text to remind myself that pin 1 is ground. And I'll hold Alt to go to a finer resolution. And once I've got that at the right grid, now I'll copy it, and it'll stay at that 0.1 inch spacing. Pin 2 is VCC. So these are just labels. They don't mean anything. It's just to remind myself when I solder it in which orientation to solder this in it. Okay, so that looks good. Finally, I will make a device for my display. So we'll add my display footprint, symbol. And the package is the footprint, new package, display, and connect. Pin 1 is ground, 2 is power, clock, and data. So that was the trick. Now we'll do the same thing for the snap and the USB to UART. So the snap needs 5 pins. So maybe we'll add a footprint called snap. And I'll switch over to my 1x05. And I'll group and copy. And switch back to my snap. And again, I don't really need the silk screen that they gave me, so I'll turn off my non-silk screen things, group the silk screen, and delete it. And pin 1 on the snap has a triangle on it. So I'm going to draw a triangle at pin 1 so that I remember that that is pin 1 when I try to plug everything in. Maybe I'll even shorten this up a little. Okay. Okay, the display, the pick, the snap, the USB to UART. USB to UART. Oops. Six-pin connector. Group. Copy. Paste. And delete. Show. Okay, again, this is another chip that I want to make sure I don't plug in backwards. So I'll put some text in. Try to center it the best I can. I'm not going to label every pin. I'll just label the side pins so that when I go to plug it in, I know the orientation. Okay, and finally, the voltage regulator, I think. This is a 4-pin device, actually. Okay, so what did I do? I made V out pin 1. Draw a box around this guy. Looks like the middle. Let's see, so that's 0.4 wide, and what do we need? 0.5. 350 would make it 0.4, so this should be 450. Let's make this one 0.5 long. Okay, let's take a look at how we're doing. We've got our voltage regulator. We've got, the voltage regulator. We've got the snap. We've got the PIC. We've got the USB UART. We've got our display. Now we need the slide switch. That's something we have to make from scratch. Let's do that. The slide switch has 6 pins. How we're going to treat it is that the middle pins will be the output. The outside pins will be inputs. So the top pin will make 6 volts from battery. And so when the slide switch is when we move the slider up, that will connect pin 1 to pin 2. So 6 volts will come out of the input. When we slide it down, pin 2 will be connected to pin 3 instead. That's where 5 volts will go. So that's how we'll select between the battery and the 5 volts. I'm pretty sure in this version of the switch, the left side and the right side are independent. So I'm also going to connect pin 1 and 6 together, pin 2 and 5 together, pin 3 and 4 together, so that I get really one switch, not 2 independent switches. What we really care about are how big those holes should be. So the datasheet says that the diameter of the holes should be 0.9 millimeters with 3.3 vertical spacing and a 2.5 millimeter horizontal spacing. So first we'll make the symbol. I'm going to call it slide. And maybe this time I'll try to make it more like a slide switch. So we'll have 1, 2, 3. What did I do? 1, 2, 1, 2, 3. Pin 1 is an input pin. Pin 2 is an output pin. Pin 3 is an input pin. Pin 4 is an input pin. Pin 5 is an output pin. Pin 6 is an input pin. I'll give this a name and a value. I might have forgotten to do that in some other ones. We can go back and fix that. We'll draw our box. So here is our little slider. You can move up and down. And here's our box around our pins. Okay, save that. Now we need to make that footprint. So far we've been working in inches, so let me change to millimeters. But I'm not going to change my grid spacing. Kind of like working at the 0.1 inch spacing, that's what breadboards have. So I'll draw a pad. I want it to be a circle, and it has a 0.9 millimeter drill, and we'll let the green part, what they call the diameter, be auto. 3, 4, 5, 6. Actually, I kind of want this one to be pin 1, 2, 3, 4, 5, 6. Now I just have to get the spacing right. In this vertical direction, they're supposed to be 3.3 apart. So to be symmetric, that would be 1.65. Minus 1.65. And then horizontally should be 2.5. Save. So I've yet to find a good slide switch that fits in a breadboard. They all seem to be kind of metric. Okay. Then this actual device is 9 millimeters long and 3.6 wide. At this point, I'll switch back to mils, because I like having 16 mils thick lines. Why not go back to millimeters, get the sizing right. So what did we say? It was 9 by 3.6. So half of 3.6. 1.8. And 9 would be 4.5. And why not? I'll draw a little box showing where that slider should be. Two, three, four, five, six. Okay, I've got my slide switch. Next up, I need some holes in my board so I could solder in power from this battery. That's just 2 pins next to each other. So I'll make a pretty simple component for that. I'll call it battery. 2 pins. I'll make pin 1 ground and pin 2 the bat. Put a name. Give it a value. The battery, I'll just go copy the 2 pin from SparkFun. Let's see. Group. Copy. Paste. Hide. Delete. Show. Okay, what did I say? 1 was ground. Let's play with the size a little. Should I draw a box around it? Might as well. Okay, that'll be our little battery connector. And kind of important here that I remember that pin 1 is ground. So when I connect, pin 1 should be ground because I labeled pin 1 as ground. Okay, so we have a battery, goes to the slide switch, goes to the regulator, got the snap, the pick, our display, communication. Now we need 2 buttons and 2 LEDs and then resistors and capacitors. Let's take a break from making stuff. Let's go grab the LEDs and the resistors and the capacitors. So Eagle does have some nice libraries for those things. If we go into the Manage Libraries section, and I'll click on it and type L, will bring me to an entire LED library. And then there's an LED device that is a schematic for an LED and then a bunch of different LEDs. We're using 3mm LEDs, so I'll grab the whole thing. To library. Then we want a resistor, capacitor, inductor library. I'm going to grab all of the US versions of resistors and all of the US versions of capacitors. Okay, so what do we just do? We just got resistor, we got capacitor, we got LED. That was easy. Now the button. So this particular push button has 0.2 inches between the leads. So I'll probably just design it from scratch. Oops. So I'll make a symbol for a button. Button has 2 pins, pretty simple. Don't even really have to name them because it's symmetric. Name and a value of our button. Now the footprint for the button is similar to a 1x03 where the middle pin is missing. So I'll grab this. And we'll do the same thing I always did before. Delete this particular silk screen. Then I don't need the middle button, the middle pin. Pin 1 and pin 2 now. And this button is, let's see, like 2 square. 2 on 2, 2 on 2. That's kind of how big the button is. Okay, so back to here again. We've got battery, slide switch, buttons, LED, resistor, capacitor. Okay, now on the sides of the boards, we're going to have 10 pins broken out. So let me make 2 5x1 connectors, just very generic. should I call it? I'm going to call it a 5, for lack of a better word. One, two, three, 4, 5, and this is just a generic 5-pin connector. It doesn't even get named. The pins don't get names. And we're gonna steal the 1x05 size from SparkFun. So these name and value tags, notice I'm not really putting in any particular place. They're movable later on. And actually, I'll probably even delete them. But just for consistency, I'll keep it. Oops, that's what I wanted. Go to here. Five pin. Connect to my made up 5-pin device. Connect it up. Last thing I think I want are some 1-pin devices. So anywhere that I might have a voltage that I want external to the board that I haven't given a pin yet, I'll drop some single holes. So I'll call that a 1. One single pin. Okay, why don't we just do it from scratch here? This is supposed to be a 40. And SparkFun says it's 74 there. Okay. So I think we've got all the components. Now we have some things that are not components. We've got a 3-volt tag and a ground tag. Might as well copy those from Eagle's library. That library is called Supply 1. So this is a symbol. It has no footprint because it's just a tag to make us very easily name our voltages. So I'll grab 3 volts and 5 volts and ground. Okay, anything that you see here is a label. That's added later in the schematic. So I think we've got all of our parts. Let me go back and look at some footprints just in case. So let's see. The display, I never added the name and the value. Do that before we forget. Now we could always go back and update these. It's not a big deal. In fact, I don't usually like the names or the values anyway, but put it here anyway. What else did we probably do? Probably forgot to do that for the voltage regulator and the USB to UART. Okay, so voltage regulator, USB to UART, the snap. I need to name the value. The thing I'm skipping here is this 3D package. Eagle has the ability to render your part in 3D. I haven't used that yet. Okay, slide switch, resistors, pick, LED, ground, 5, display, capacitor, button, battery. I'll leave the name and value off these guys. Okay, so I think that's a nice long video for how to make all the components we're going to need. In the next video, I will draw the schematic, and in the third video, we will do the layout and generate the Gerber files.